All right, folks, welcome. We're going to talk about computing the greatest common divisor of two numbers, and we're going to wrap it up with the greatest common divisor of three numbers even. But first, let's start off small, and let's even figure out what we're talking about. So the greatest common divisor, GCD, of two numbers is essentially the largest number that goes into both of those numbers evenly. For example, I know that 2 goes into both 12 and 18 because 12 and 18 are both even numbers. But the question is that the greatest number that goes into both of them? So I'm going to write equals right here, and we're going to fill in that blank with the answer. The way that I like to approach this problem is how I learned it. I call it upside down division. And so what I'm going to do is look at the prime factors of these two numbers. I'm going to do the prime factorization, the prime decomposition of these two numbers. So I need to divide prime numbers into 12. So one that comes to mind is 2. 2 is a prime number. Remember, prime numbers are numbers that are only divisible by themselves and 1. So 2 is such a number. It's the smallest prime number. How many times does 2 go into 12? 6. Now 6 is not a prime number. 6 happens to be a composite number. Composite numbers are essentially numbers that are not prime. So how many times, or what is something that goes into 6? 2 also goes into 6. It does so 3 times. Now I know that I'm done because I am left with a prime number at the end. 3 is prime, so I'm done. I'm going to do the same thing for the number 18. All right, let's start with 3. I know that 3 goes into 18. It does so 6 times. I'm not done because 6 is not prime. 2 goes into 6 3 times. I end with a prime number, and so I know I'm done. So now the question is, what is the greatest number that goes into both 12 and 18? The way you find that out is you look at what factors are common between 2 and 18. What prime factors are common? So they both have a 3. So I'm going to keep track of that. They both have a factor of 2. I'm going to multiply that up here. Now what's left? There's a 2 over here, but there's not another 2 over here. There's a 3 over here, but there's not a 3 over here. So I've exhausted everything that they have in common. So the greatest common divisor of 12 and 18 is 3 times 2, which is 6. All right? So I know now that 6 is the largest number that goes into both 12 and 18. May not seem like that big of a deal. As we deal with larger numbers, it may not be as obvious that whatever the greatest common divisor is actually the answer. So let's do another one. It's going to be another simple one. The greatest common divisor of 6 and 8. You could probably tell right now that it's going to be 2. Let's actually verify that. So I'm going to do the prime decomposition of 6. We already did that up above. It's 2 times 3. I end with a prime number. 3 is prime, so I'm done. I'm going to do the same thing for 8. 2, which is prime, goes into 8 4 times. 4 is not prime. 2 goes into 4 twice. I end with a prime number, so I'm done. And so my greatest common divisor is 2. And there's nothing else that these two numbers have in common in terms of their prime factors. And so my answer for the greatest common divisor of 6 and 8 is in fact 2. So once you get the hang of it, this process is pretty simple. So let's do the greatest common divisor of 210 and 360. All right? So we're upping the ante a little bit. It may not be as obvious. What I like to do when I teach things is also address common mistakes. I teach math at the college level, and whether it's your most basic mathematics or whether it's differential equations or even beyond, I still see the same mistakes and the same errors coming up time and time again. And if students could just rid themselves of these very common mistakes, they'd be pretty much set. Math would not be as intimidating. Math would not be as difficult. So one thing that I think a lot of students might see here is two numbers that both are divisible by 10. While that is the case, that is certainly true because these numbers end in zeros. The problem with that is 10 is not prime. 10 is a composite number. It's 5 times 2. So if a student were to start the prime factorization with 10, they would ultimately be wrong because 10 is not prime. So you got to step back and make sure you're only factoring out prime numbers. All right, so I indicated that 10 goes into 210, and that's a 0, not a 6 at the end. And so let's not factor out 10, but let's factor out a 5 from 210. Okay, how many times does 5 go into 2? Well, it doesn't. How many times does 5 go into 21? 4 times, with 1 left over, and 5 goes into 10 twice. So 5 times 42 is 210. 42 is not prime. Most certainly is not, because I know that 2 goes in there because it's even. 21 times. 21 is not prime because 3 goes into it 7 times. 7 is prime, so I stop right there. All right. The prime factorization of 210 is 5 times 2 times 3 times 7. Let's do the same thing for 360. Again, I'm not going to divide 10 into that, or 180, or anything else that's not prime. So let's just start easy and do a 2. It's an even number. 360 is even, so I know that 2 will go into it. Happens to go into 180 times. Let's factor out another 2 because that's still even. And I get 90. 90 is even, so I know that 2 goes into it. I get 45. 45 is not even, but 45 is also not prime because 5 goes into it 9 times. 9 is not prime. It's 3 times 3. So there is the prime factorization of 360. 360 is 2 times 2 times 2, or 2 cubed, times 3, or 3 squared, times 5. If you want to represent these numbers as a prime decomposition, you would certainly write that, right? There's 2 times 2 times 2. So when you multiply something by itself 3 times, that's a cube. 3 times 3 is 3 squared, and there's a 5 all by itself. So this is a little side note, but this would be the prime factorization of 360. At any rate, we're going to see what they have in common. They have a 5 in common. Cross those out so we can keep track of them. I'm going to write a 5 up there. They have a 2 in common, like so. They have a 3 in common. There's a 3 right there and a 3 right there. And the only thing left here is a 7, and there's no 7 in 360. And so the prime factorization is 5 times 2, which is 10, times 3, which is 30. So it may not have been abundantly clear just by looking at 210 and 360 that the largest number that goes into both of those numbers is 30. Certainly 10, we saw that kind of from the get-go, but we can do even better. That's what the G means. The greatest common divisor, the largest thing that can go into both of these numbers, is 30. All right, let's do another example. Let's do the greatest common divisor of 2 perfect squares. Here it's going to be 25 and 16. All right, pretty simple to see what the prime factorization of 25 is, because 5 goes into 25 5 times. 5 is prime, so I'm done. Again, we don't want to start with dividing this out by 4. I agree, 16 is 4 times 4, but the problem with that is 4 is not prime. 2 is prime. 2 goes into 16 8 times. Factor out a 2. 2 goes into 8 4 times. 4 is composite. It's 2 times 2. I end with a prime number, and I'm done. Okay? So, now we start to cross off the things that they have in common. Well, there's only 5s here, and there's only 2s here. They have nothing in common. Here's another mistake that students are going to make. They're going to see this, and they're going to panic, and they're going to say, well, the greatest common divisor is 0. And that's really not the case, because 0 is not a divisor. In this case, the largest number that can go into both of these numbers, since they don't share anything in common, is 1. All right? Now, you may have heard the term relatively prime, and that's certainly the case with these two numbers. They are not prime numbers, but relative to one another, since they share no common divisor other than 1, we call these two numbers relatively prime. All right, so you know that you have a relatively prime number if the greatest common divisor of those two numbers is 1. All right, let's do another example. Let's do the greatest common divisor of, let's do 3,600 and 4,320. All right, yes, we are up in the ante quite a bit here. So we're just going to start off the same way. We're going to start our prime factorization. That is certainly even. So I'll start with a 2, and I get 1800. Pull out a 2, I get 900. Pull out a 2, I get 450. I'm running out of room, so I'll go ahead and pull another sheet of paper out here. That's still even. Pull out a 2. 2 goes into 4 twice. 2 goes into 5 twice with 1 left over. 2 goes into 10 5 times. And now that is not an even number, so I can't pull out a 2, but it ends in a 5, so I know that 5 is a prime factor of 225. 5 goes into 22 4 times with 2 left over. 5 goes into 25 5 times. 45 is not a prime number. 5 goes into it 9 times. 9 is not a prime number because 3 goes into it 3 times. 3 is a prime number. So you can see quite the prime factorization of 3,600. All right, we're done. We've ended with a prime number, so we're going to do the same thing for 4,320. It's even, so I'm just going to make life easy on myself and start off with pulling out a 2. 2 goes into 4 twice. 2 goes into 3 once with 1 left over. 2 goes into 12 6 times. 2 goes into 0 0 times. I get an even number, so I can do that again. 2 goes into 2 once. 2 goes into 1 0 times with 1 left over. 2 goes into 16 8 times. 2 goes into 0 0 times. I get 1,080. I'm not done. I'm not done because that's an even number. 2 goes into that. 2 goes into 10 5 times, and then a 4, and then a 0. Still even. All right, you can see that when you have an even number, it's pretty simple to see what one of the next prime numbers might be. 2 goes into 5 twice with 1 left over. 2 goes into 14 7 times evenly. 2 goes into 0 0 times. I still have another even number. And 2 goes into 2 once. 2 goes into 7 3 times with 1 left over. 2 goes into 1 5 times. All right, not a prime number. 5 goes into that, certainly, because it ends in a 5. All right, 5 goes into 1 0 times. 5 goes into 13 twice with 3 left over. 5 goes into 35 7 times. Now things are a little bit more manageable, a little more obvious to see that 3 goes into 27 9 times, and I end with 3 times 3, which is 9. So quite the list of prime factors. And so really, if you're a student that knows what's going on, you've probably made it this far. If you're going to make a mistake at this point, you're probably just going to lose track of how many prime factors you have. All right, so just be very careful, be very neat and tidy and meticulous about your work. That's another common source of error that I see students make, is they just want to rush and get through it. And they're going to miss something along the line. They're going to drop a 1, they're going to forget a negative somewhere. Keep your work neat and orderly, and you'll be a lot more successful. So let's start crossing off some of these common factors. They both have 2's. They both have more 2's. And then another factor of 2. And then another factor of 2. All right. They have a common factor of 5, like so. They have a common factor of 3. They have another common factor of 3. And the only thing left here is a 5. And the only thing left here is a 2 and a 3. So they no longer share any common factors. And so let's see if I can even do this in my head. I have 2 times 2 times 2, which is 8, times another 2 is 16, times 5 is 80, times 3 is 240, times another 3, I believe, is 720. And I did that in my head. Honest to goodness, I don't have an answer to here, and so I would be amazed if I did not make a mistake. So I want to end this video with one problem where we're actually going to compute the greatest common divisor of three numbers. How do you do that? Well, the process is the same. So if you've been following along with what we've done so far and you understand this prime factorization, this decomposition of numbers into their prime components, their prime factors, then the process is exactly the same. So we're going to find the largest number that goes into 546 and 28 and 315. All right, so may not be obvious right now. So let's just start with 546. It's an even number. I'm just going to make things easier for myself and factor out a 2. 2 goes into 5 twice with 1 left over. 2 goes into 14 7 times evenly. 2 goes into 6 3 times. Now, that 273 makes me nervous because I may not see right off the bat what a prime factor might be. So here's a little trick. When faced with a number like this, if it doesn't end in an even number, so it's not a, 2 doesn't go into it, and it doesn't end in a 5 or a 0, so I know that 5 doesn't go into it, my go-to at this point would be to add up the digits that I see, which is 2 plus 7 plus 3, which is 12. When you add up the digits of a number, if that sum is divisible by 3, then this number that you started with is also divisible by 3. And that's true for a number of any size. If you add up the digits of that number and that sum is also divisible by 3, then that number that you started with is divisible by 3. So it's a really nice trick when you're trying to figure out the prime decomposition of a number. I know that since 2 plus 7 plus 3 is 12, and 12 is divisible by 3, that means that 273 must also be divisible by 3. Now, that's only a trick for 3s. Don't start thinking you can do this with 7s and 9s and stuff like that. It's special, it's unique to 3, so don't go around saying, hey, the numbers are divisible by 7, so that means that 7 must go into this number. That's not the case. So 3 goes into 27 9 times evenly. 3 goes into 3 1 time. And I get 91. Now, 9 plus 1 is 10. That's not divisible by 3, so 91 is not divisible by 3. It's not an even number. It doesn't end in a 5, so my tricks were sort of exhausted. But 91 is not a prime number. I've chosen this problem for the end because it's one of these numbers that's not obvious. 7 goes into 91. 7 goes into 9 once with 2 left over. 7 goes into 21 3 times. Now 13 is a prime number, and so I stop right there with 546. Let's do the same thing for 28. It's even. Let's start off strong. 14. 2 goes into 14 7 times, and I am done because 7 is prime. Let's do 315. Certainly divisible by 5 because it ends in a 5. 5 goes into 31 6 times with 1 left over. 5 goes into 15 3 times. 63 is not a prime number. It's composite because 3 goes into it 21 times. And 3 goes into 21 7 times, and I am done. So we're at a point now where we look across all these numbers and we see what they have in common. So they certainly have a 7 in common. Right there. There's a 2 here. There's a 2 here. But there's not a 2 here. There's a 3 here, and there's a 3 here, but there's no 3 right here. There's a 5 here, but there's no 5s here. There's no 13s. So these numbers only have one factor in common amongst all 3 of them. The largest number that goes into all 3 of those numbers is 7. So that would be the greatest common divisor of those 3 numbers. Finally, the only way that you're going to get good at math is if you practice, practice, practice. And so I'm going to end each of my videos with a list of problems for you to practice, and I'm going to put the answers, not the full solutions, but the answers to these problems in the comments below. So if you've enjoyed this video, if you learned something from it, please be sure to like it. I'm going to come out with a lot of math videos from basic math up until calculus, up until differential equations, linear algebra, anything that you want to know, send me a message, comment. I will make videos for it. I love teaching math. I love helping people with math. And so I'm happy to make whatever videos that I can. I'm going to mention the common mistakes so that you don't make them. And I appreciate you watching. Again, don't forget to subscribe. Don't forget to like. And thanks for watching.